Real Gas Mixtures Explained, Don't Let This Cost You Points on Your Exam, Part 2, is an episode of the Degrees of Freedom Project, videos on chemical and thermal principles. Definitions and additional details can be found at the webpage link in the description. This video assumes knowledge of Real Gas Mixtures Explained, Don't Let This Cost You Points on Your Exam, Part 1, and continues with an example. As a review, K's rule has the following steps. 1. Calculate the pseudocritical temperature. 2. Calculate the pseudocritical pressure. 3. Calculate the pseudo-reduced temperature. 4. Calculate the pseudo-reduced pressure. 5. Use the generalized compressibility charts to calculate the mixture compressibility, ZM. 6. Use ZM to calculate anything else needed. Again, with the generalized compressibility charts, we used two of the pseudo-reduced temperature, the pseudo-reduced pressure, and the mixture compressibility to look up the remaining one, and use that value to calculate our answer. Once we posed the example problem and solved it with the ideal gas law and then K's rule, we'll demonstrate how to use it with the Peng-Robinson equation to calculate the answer, and then report the results for Soave-Redlich-Kwong and Lee-Kessler-Plucker as well. So let's work the example with K's rule. Let's say we have a stream of 20% methane, 30% ethane, and 50% propane at 423 K and 70 atm flowing at a rate of 100 kmols per hour. We want to estimate the volumetric flow rate with K's rule and compare it with the ideal gas and several equations of state. This example is at the same temperature, pressure, and flow rate as the real gas example in When Getting Gas is an Ideal Part 2. The difference is that we have a mixture of light alkanes instead of pure propane. First, from Wikipedia, we find for methane that the critical temperature is 190.56 K, and the critical pressure is 4.5992 megapascals. We find for ethane that the critical temperature is 305.2 K, and the critical pressure is 4.8714 megapascals. And we find for propane that the critical temperature is 369.9 K, and the critical pressure is 4.23 megapascals. Since the critical pressures are in megapascals, we will convert 70 atmospheres to 7.093 megapascals, or 7,093,750 pascals. The ideal gas calculations have not changed from When Getting Gas is an Ideal Part 2, because we're at the same temperature, pressure, and molar flow rate. V hat equals RT over P is calculated here in both the SI units of meters cubed per mole and in liters per mole. Then the volumetric flow rate is the molar flow rate times the molar volume, giving almost 50 meters cubed per hour. We don't have an empirical value with which to compare, so we will use the Peng-Robinson equation to calculate the closest thing to the truth. For K's rule, we calculate the pseudocritical temperature as 314.7 K and the pseudocritical pressure as 4.496 megapascals. From those values and the system temperature and pressure, we calculate the pseudo-reduced temperature as 1.344 and the pseudo-reduced pressure as 1.577. As a reminder, reduced temperatures and pressures are dimensionless. Now for the generalized compressibility chart, we have the reduced pressure as 1.577 and the reduced temperature as 1.344. We then draw a line up from PR equals 1.577 to the TR equals 1.344 curve. Then we draw a line over to ZM and read off 0.7833. I again use my Lee-Kessler spreadsheet to calculate ZM rather than read it off the chart. You have to read it off the chart, and you probably won't get 4 significant figures. You'll probably get 2 1/2 at best. Finally, the K's rule flow rate is ZM times V dot ideal gas, or 38.84 meters cubed per hour. Here is a brief demonstration on how to use DWSim. We first need to convert 100 kilomoles per hour into moles per second. We multiply by 1,000 and divide by 3,600. The result is 27.7 repeating moles per second. We start up DWSim by double-clicking and waiting for the startup screen. Under Process Modeling, we look for Create New and click on it. Once the Simulation Setup wizard appears, we click Next. In Step 1, we will add our 3 hydrocarbons. In the search box, type methane and hit Return. Click on methane. Then type ethane in the search bar and hit Return. Click on ethane. Methane is showing because the word methane contains the word ethane. Finally, type propane in the search bar. Hit Return and click on propane. Now click Next. In Step 2, click the My Process Deals with Hydrocarbons Only radio button and click Next. In Step 3, enter a name for the simulation. This is where you change the set of units. The C1 and below let you specify a custom set of units. We're not going to worry about that right now. Click Finish. Now, so that we can use all three equations of state, we're going to the setup menu and choosing basis. In the thermodynamics tab, it has Peng-Robinson, PR, already listed because that's the default for hydrocarbons. Click on Add New Property Package and choose Suave Red Liquang, SRK. Repeat the process and choose Lee Kessler Plucker. Then close the window. It's a little disconcerting there is no next, save, or close button. Down towards the bottom of the screen, you will see the Material Stream button. Click and drag a material stream onto the PFD window. It will be very small and have the clever name of 1. Repeat the process and drag streams 2 and 3 fairly close to stream 1. Now find the Zoom to Fit button and click on it. Click on Stream 1. In the side window, notice that the property package is Peng-Robinson. Leave that as is for now. Set the temperature to 423 K and the pressure to 7,092,750 megapascals. Set the molar flow rate to 27 point a whole bunch of 7s and an 8. Scroll down to the mixture composition and set methane to 0.2. Ethane to 0.3. And propane to 0.5. Then click on Accept/Update. The sheet should automatically recalculate, but I usually click on the Solve Flowsheet button at the top to make sure. Repeat entering the data for streams 2 and 3. Except set the property package for stream 2 to Suave Red Liquang and for stream 3 to Lee Kessler Plucker. Hit the Solve Flowsheet button one more time for good measure, then click on the Results tab. Click on Stream 1 and observe that the property package is Peng-Robinson, then find the volumetric flow rate. You'll need to multiply it by 3,600 to get it in meters cubed per hour. Search down lower to find the value for compressibility for the mixture. Repeat the process by clicking on Stream 2 and then Stream 3. These results have been pasted into the results spreadsheet. We use Peng-Robinson as the true value, since we don't have empirical data for a true value. Here is a spreadsheet comparing the results. There is a link to it on the video website in the description. The blue quantities are reference values, the green quantities are given in the problem statement. If we assume Peng-Robinson is correct, and it should be very close for an aliphatic hydrocarbon mixture, ideal gas is 28% high, SRK is 2% high, Lee Kessler is 2.5% high, and K's rule is under 1% high. Because this is a mixture of aliphatic hydrocarbons, everything but ideal gas is pretty good. If you had different species, like water and alcohol and an aromatic hydrocarbon, you would see quite a bit more difference, and K's rule wouldn't be that good. Lee Kessler Plucker would probably be the best. The takeaways from this video are: 1. K's rule is the simplest method for calculating properties of mixtures of real gases by hand, and it is very good for aliphatic hydrocarbons, but it is still a fair amount of work. 2. DWSim or some other software application is the easiest way to calculate properties of mixtures of real gases using equations of state. 3. Life gets much more interesting than the ideal gas law when you have mixtures of real gases. Thanks for watching. This video was brought to you by the DOFPro team.